welcome back. Today we're going to be continuing our explorations of sequences of real numbers and talk about a very important description of sequences known as monotonicity of those sequences, right? So let's introduce the set of definitions that we're going to be working with today. So we're going to be saying that a sequence is increasing if the first term is less than or equal to the second term, is less than or equal to the third term, is less than or equal to the nth term, and so on. Generally speaking, an is less than or equal to an plus 1 for all n in its domain. And we say that the sequence is strictly increasing if an is strictly less than an plus 1, again for all natural numbers in its domain. Similarly, we will say that that sequence is decreasing if a1 is greater than or equal to a2, is greater than or equal to a3, greater than or equal to an, greater than or equal to an plus 1, and so on, and strictly decreasing in a similar way. And overall, if it is either increasing or decreasing, we will say that that sequence is monotone, or we will also say that that sequence is monotonic. And if that sequence is either strictly increasing or strictly decreasing, then we will say that that sequence is a strictly monotonic sequence, or that that sequence is strictly monotone. All right, so that's what we're going to be talking about today. So let's start off with a few examples to see if we can justify whether a sequence is monotone, either increasing or decreasing. The first sequence is actually quite an important one, and that's going to be equal to an is equal to 1 over n, and as usual we're going to be taking the domain to be 1 to infinity. So what type of sequence is this? Well, if you sort of look at the domain and look at the sequence values, when you plug in 1, we're going to have 1 as our output. And then we're going to have 1/2, 1/3, 1/4, 1/5, and we're going to have this particular sequence. So you may see that, okay, well maybe this is going to be a strictly decreasing sequence, moreover a strictly monotonic sequence. So how are we going to prove that this is indeed the case? Right? So we already know that if n is a natural number, moreover if n is a real number, we know that n is always going to be strictly less than n plus 1. So what I want to do is I want to divide both sides by n times n plus 1. Also, if n is a positive number, that means also n plus 1 is a positive number, which means that n times n plus 1 is also going to be a strictly positive number. Therefore, when we divide by this little quantity, our inequality sign will not change directions, right? So once we simplify this little expression that we've constructed, then we have that 1 divided by n plus 1 will be strictly less than 1 over n. Right? And obviously that's going to be equivalent to saying that 1 over n is strictly positive than 1 over n plus 1. And that precisely is an, and that is just an plus 1. So that we have an strictly greater than an plus 1, and that's obviously true for all natural numbers n. And that by definition proves that an is a strictly monotonic decreasing sequence, right? So therefore an is strictly decreasing, right? And that's practically how proofs of strictly increasing, strictly decreasing are going to go, right? So that's a very nice little sequence. Let's see if we can do another one that also has quite a few applications. Let's look at the sequence 1 over n factorial, and let's call that again an. And as usual, n is going to range from 1 to infinity. So this is going to be similar to 1 over n in the sense that this is a strictly decreasing sequence, right? So just a couple notes in case you don't remember anything about factorial. N factorial is going to be equal to n times all of its preceding natural numbers. N times n minus 1 times n minus 2, n minus 3, all the way down to 3 times 2 times 1. And that's going to be true for only the set of natural numbers. And there is a special case that 0 factorial is equal to 1. But we do not necessarily need this here because we're starting at 1, not 0, right? But it's useful to keep in mind that 0 factorial is commonly defined to be equal to 1, right? So let's see if we can prove that this sequence is a strictly decreasing sequence, i.e. a strictly monotone sequence also, right? So if k is less than n, and let's assume that k and n are natural numbers. What can you tell me about n minus k? Is this going to be positive or a negative number? So if k is less than n, then practically all we need to do is just subtract k from both sides, and we see that n minus k is always going to be a strictly positive number. And that's obviously true for k in the set of natural numbers where k is less than n, right? So if that is the case, then what exactly do we have? So if we have n minus k plus 1, n minus k plus 2, or those k plus 1 and 2s are in parentheses, then which of these is going to be the greatest one? Because we're going to have m minus 1, m minus 2, m minus 3. Obviously, that's the greatest of this particular sequence, and if we have n that precedes that, so if we allow k to be 0, then n minus 0 would be the greatest in that sequence, right? So practically what we have here is a sequence of positive naturals, right? And if we multiply a sequence of positive naturals, we will also get a positive natural as well, right? So let's sort of state that out. So n factorial is just a product of positive terms. Moreover, they're greater than or equal to 1. Okay, so what does that mean? So that means n will be less than n times m minus 1, and that's going to be less than n times m minus 1 times m minus 2, and we can continue this all the way down to n factorial in an inductive fashion if needed, right? So what we have here is a strictly increasing sequence, right? But it's not the sequence that we want, okay? So what we can do is we can practically divide or reciprocate each of these terms and then reverse our inequality, right? Because remember, if a is less than b, where a and b are non-zero, then that means 1 over a is going to be greater than 1 over b. That's one of the properties of the reals. So if that is the case, then once we reciprocate, what we're going to have is 1 over n factorial is going to be less than 1 over m minus 1 factorial. So I'm starting at the top and working my way left. And that's going to be less than 1 over m minus 2 factorial. And that's going to be true all the way down to 1 over 1 if we can continue inductively. So that gives us 1 over m plus 1 factorial will be less than 1 over n factorial. And what is exactly this? Well, that's just an, that's just am plus 1. So we have that am plus 1 is strictly less than am. And we can equivalently say that that's true equivalently to an is greater than am plus 1, and that's true for all natural numbers m. So if that is true, then what do we have? So that means 1 over n factorial from n is equal to 1 to infinity is a strictly decreasing sequence. And since it's either strictly decreasing or strictly increasing, that means it's a strictly monotonic sequence, right? So those two are definitely very useful sequences to be able to prove, and I'll list out a couple more examples because I think these examples are also pretty nice. In particular, if you have 2 to the n and the nth root of 2, again, where n ranges from 1 to infinity, and again ranges from 1 to infinity, this is going to be a strictly increasing sequence, and this is going to be a strictly decreasing sequence. And I'll leave these two exercises for you to try on your own. A theorem that I want to introduce for monotonic sequences is very, very important because it establishes a biconditional for convergence, provided that it is bounded, right? And it says the following. So a monotone sequence of real numbers converges if and only if it is bounded. So if it converges, it is bounded. If it is bounded, it converges, provided that the sequence we're working with is a monotone sequence, right? So monotone sequence is true as premise, and then we're going to show that convergence implies bounded and vice versa, right? So let's see how we can prove this, right? So we're going to begin by letting an, from n is equal to 1 to infinity, be a monotone sequence. So it can either be increasing or decreasing. I don't care which one it is, right? So let's see if we can prove this direction, right? So we're going to be assuming, so suppose that an converges, right? So one of the theorems that we proved last time when we first started talking about sequence is that if this sequence converges, that means there exists an m in the set of positive reals such that the absolute value of am is less than or equal to m. Right, so that's the bounded convergence theorem for sequences, right? So if it converges, that means it's bounded, both above and below, right? So if that's the case, then we have that an is bounded, and that is the conclusion from left to right, right? So that is the left to right part of this proof, right? So now let's see if we can prove it in the other direction. In particular, let us suppose that an is bounded, and we're going to show that this implies that the sequence converges, right? And keep in mind, an is also a monotone sequence, right? So if it is bounded, then what does that mean? So that means that the absolute value of an is less than or equal to m for some positive real number, right? Some positive real number, and that's going to be true for all n in the set of naturals, right? So our question then says, so the question that we aim to solve, is this enough to show that the limits of this sequence exist? Right? Because if it does exist, that implies convergence. Okay? So if the absolute value of an is less than or equal to m for some positive real number, that means that an is bounded above, and it's also bounded below. Okay? So if it is a bounded subset of the reals, then what do we know exists? So by the completeness axiom of the set of real numbers, that means that the supremum of this sequence, and let's call this supremum alpha, also belongs to the set of real numbers, right? That much we do know. And also, not only is this, so we're just using the bounded above property to imply that the supremum exists. Equivalently, since it's bounded also below, that means the infimum exists, right? So we're going to have a two-case proof here. So what we're going to do now is we're going to assume that since an is monotonic, we're going to assume that an is increasing. And you can do similarly, we can do the following for decreasing, right? Because it's monotonic, so it's either increasing or decreasing. So that's your case 1, case 2, right? So we're just going to be working with the case that is bounded above, and the supremum exists by the completeness axiom, and we're going to assume that it's increasing. And so if you assume it's decreasing, you still have that the infimum exists, and it's also bounded below, so you can use that direction as well, right? So let's assume that the sequence is increasing, and we already have justified that the supremum exists in the set of real numbers. So what are we going to do? So we're going to be letting epsilon be greater than 0. So if alpha is the supremum, that means it's the least upper bound of that sequence. What can you tell me about alpha minus epsilon? Well, if alpha is an upper bound, and we're in the subset of the real numbers, and it's also the least upper bound, right? That means alpha minus epsilon is not an upper bound. It's not an upper bound because alpha should be the least of the sequence am, right? So if that is the case, that means that there exists some term of that sequence, right, such that alpha minus epsilon is less than ak, right? Because if it's not an upper bound, that means there's a term of the sequence that's above this number, alpha minus epsilon, right? And that's going to be true for some k in the set of real numbers. As to which one it is, we don't know, but we do know that it does exist, okay? So if that is true, what do we know? So therefore, since an is increasing, then we know that ak is less than or equal to an, and that's going to be true for all n bigger than or equal to k. And of course, if you're trying to prove this for the decreasing version, then you're going to have that ak is greater than or equal to an for all n greater than or equal to k. Right? So if that is the case, then what do we have? So we already have that alpha minus epsilon is less than ak for some k in the set of natural numbers. We have that an is an increasing sequence, so we know that ak is less than or equal to an for all n greater than or equal to k. We know that alpha is the least upper bound, so we know that an is always going to be less than alpha, and by properties of reals, we know that alpha is going to be less than alpha plus epsilon. So practically what I'm doing is I'm bounding our sequence an. Right, so we have that an is between alpha minus epsilon and also alpha plus epsilon. So what we've done is we've created this sequence of inequalities, and from it we can say that an minus alpha is going to be strictly less than epsilon, and that's going to be true for all n greater than or equal to k in the set of natural numbers. And by definition, what does that mean? That means that the limit of an is equal to the supremum of that set, and that means that an converges, which is what we sought out to prove. Right, and the proof for the decreasing case is actually not quite hard. It's practically the same exact proof. And I want to just mention a very important corollary to that, and that's the following. So if an is not bounded, and let's assume that it's also monotonic, then what can you tell me about am? Is it possible that it converges? No. Right? So if it's not bounded and it's also monotonic, and when we say not bounded, that means it's not bounded above, not bounded below. Then if that is the case, then we have that sequence diverges. And this sometimes is called the monotone convergence theorem for real valued sequences. So up to this point, we know what monotonic sequences are, and we have a theorem that in some sense establishes convergence, provided that that monotonic sequence is bounded. Okay, so what I want to do is I want to introduce this very interesting example that actually has quite a few numerical analysis applications, especially to square roots. So let us assume that alpha is a positive real number, right? So here this alpha is going to be a positive real number, and we're going to consider the sequence that starts with an initial condition, a1, that is also positive, and this can be any real number as well, and am plus 1 will be defined to be half of the preceding term and alpha divided by the preceding term added up, and that's going to be true for all natural numbers m. Right? So this is obviously a sequence of real numbers. So the first question you might be thinking is, does this sequence converge? And if it does converge, what exactly does it converge to? So a couple little things that I want to do first. I want to first solve or rearrange this equation or relation for an the best I can. So you can easily get a common denominator for that expression and get rid of all of your fractions. Once you do that, you're going to have the relation an squared will be equal to 2an times am plus 1 minus alpha. Right? So if you look closely to this expression, what you have here is practically a quadratic equation in terms of am. And to make that even more clear, if we rearrange, we can write this as an squared minus 2am plus 1 am plus alpha is equal to 0. So here an is my variable. So we have variable squared minus some real number plus some real number, and that's equal to 0. And we can apply the quadratic equation to this particular relation, right? So what does this exactly mean? So that means AN is a solution to this quadratic relation. Right? So if it is a solution to this quadratic relation, we have the quadratic formula to represent it. In particular, AN is going to be equal to negative b, so that's going to be 2am plus 1 plus or minus the square root of b squared, so it's going to be 4am plus 1 squared minus 4a and then c, and that's going to be all over 2a. Right? So once we simplify this by factoring out a 4, taking the square root, which is going to be equal to 2, everything has 2 in it, so they can all cancel. What you're just going to be left with is am plus 1 plus or minus the square root of am plus 1 squared minus alpha. Right? So that's what an is equal to. Right? So it's potentially equal to two different numbers. And since an is a real number, what can you tell me about the discriminant of this quadratic relation? So if it is a real number, that means that am plus 1 squared minus alpha must be a non-negative quantity, which means that am plus 1 squared must be greater than or equal to alpha. And we've already assumed by definition that alpha is a positive quantity. Right? And if am plus 1 squared is greater than or equal to alpha, and that's obviously going to be true for all n bigger than or equal to 2, that means that an squared is also greater than or equal to alpha, and that's also greater than 0, and that's going to be true for all n in the set of natural numbers. Right? So if an squared is bounded below, that means an is also bounded below. Right? So that means that an squared from n is equal to 1 to infinity is bounded below by alpha. Right? So if an squared is bounded below, an is also going to be bounded below. And by the monotone convergence theorem, what do we have? So if an, well, all we know is it's bounded, but we don't know it's monotone, right? So if this is actually decreasing, increasing also works too, then we will have that it converges, right? So we need to somehow show that this particular sequence is decreasing. If so, we're practically done, right? So how are we going to prove that this sequence is decreasing? So decreasing means that an will be greater than am plus 1, and that has to be true for all n in the set of natural numbers. And if that is true, that means an minus am plus 1 will be greater than 0. So let's see if we can justify this, right? Because we have bounded, if we have decreasing, that implies convergence, and then we can sort of see or find out or explore what it might converge to. So what we have here is that am minus am plus 1 is going to be equal to what? So it's going to be equal to an minus the definition of am plus 1, which is defined recursively already. That's going to be equal to 1/2 of am plus alpha divided by am. Right? So we can distribute this negative sign, and we can also get a common denominator for that 2m, and that's going to give us 1/2 times, and then we're going to have 2am minus am minus alpha over am, and then we can get a common denominator by multiplying top and bottom of those expressions by am, and that's going to give us some an squared terms in the numerator of the left two terms. So we're going to have 2an squared minus an squared. That's just going to be 1an squared. So we're going to have that this is going to be equal to 1/2 times an squared minus alpha all over am. Right? And what can we say about this? Because we're trying to show that this is greater than 0. Right? And we've already proven that this sequence, an squared, is bounded below by alpha, which means that the top is going to be greater than or equal to 0. Right? And we already know that an is going to be greater than alpha, an is also going to be greater than or equal to the square root of alpha, and that's going to be strictly greater than 0 because alpha is chosen to be a non-negative quantity, so the square root can't be 0, right? So we have a positive divided by a non-negative, so that's obviously going to be greater than or equal to 0 for the difference between these two terms. Right? So what we have here is that the sequence an is a decreasing and also bounded below and moreover convergent. So it's a decreasing and convergent sequence. Right? Now the more important question is, okay, so if it is a convergent sequence, what does it converge to? So it converges to what? Exactly. Right? So let's suppose, since it does converge, let's define its limit. So let's call the limit of am, let us call this L, and we already know that this is going to be a non-negative quantity, more over a positive number. Right? So if that is the case, what is the limit of am plus 1? So we already know by properties of limits that's going to be equal to the limit of am, and by definition the limit of an will be equal to the limit of 1/2 of am plus alpha over am. And we can distribute this limit over sums, products, quotients, and scalar multiples because those are the algebraic properties of limits, right? So once we have that, what exactly do we have? So we know that the limit is going to be equal to L, that's going to be L, that's going to be L. So we're going to have that L will be equal to 1/2 of L plus alpha over L. And if we rearrange this a little bit, just multiply both sides by 2, get a common denominator with L in that term, what we're going to have is we're going to have 2L is equal to L squared plus alpha over L. Multiply both sides by L, so that's going to give us 2L squared is equal to L squared plus alpha. And then we're going to have that L squared will be equal to alpha. And then once we take the square roots of both sides, we're going to have that the absolute value of L will be equal to the square root of alpha, which means that either L is equal to the square root of alpha or L is equal to the negative square root of alpha. But the square root of alpha must be a positive number because alpha is chosen to be positive. That means L equals the square root of alpha is the only reasonable number that makes this case, right? Since alpha is bigger than 0. Right? And also the sequence is a non-negative decreasing sequence as well. Right? So we have the limit is actually equal to the square root of alpha. Right? So that's actually pretty interesting. So that means the sequence am plus 1, which is equal to 1/2 of am plus alpha over am, this sequence converges to the square root of alpha, provided that this number that you're trying to approximate the square root of is greater than 0, and the initial guess, a1, is also greater than or equal to 0 too. Right? So this is what we call our initial guess for this iteration sequence. Right? And some people will call this sequence the Mesopotamian square root sequence approximation iteration method. Several different names, but there's a couple of the common ones. Let's do a quick numerical example to sort of see how this works. So let's assume that somebody asks you, what is the square root of 7 equal to? At least by consecutive integers, we can get an integer approximation for this because we know that the square root of 7 belongs to the interval of the square root of 4 and the square root of 9 because 7 is between strictly 4 and 9, right? And we know that that's going to be equal to the interval 2 and 3, right? 2 and 3. Right? So how are we going to choose our initial guess, right? So alpha obviously is going to be equal to 7, and we're going to let a1 be equal to, you could choose 2, you could choose 3, you can literally choose anything as long as it's positive, but I'm going to choose a number that's relatively close to it. I'm going to be choosing 3, and also this has to be or it has to be greater than 0, right? But moreover, this is greater than 1, which is obviously greater than 0, right? So a1 is going to be equal to 3, that's our initial guess, and alpha is going to be equal to 7, right? So what is this going to give us, right? So a1 is equal to 3, so that means the square root of 7 is approximately equal to 3. That's usually completely misleading because we chose that a1, right? So this a2 is what is more interesting to us because we know the sequence is going to converge to the square root of 7. So a2, which is going to be equal to 1/2 of a1 plus alpha over a1, which in this case is going to be 1/2 of 3 plus 7 over 3, one can find that it's approximately equal to 2.67, right? So obviously it's a decreasing sequence. That much we've already proven. So we have that this is an approximation for the square root of 7. And if you have a calculator, you should be able to verify that 2.67 is a lot better of approximation compared to this initial condition of 3, right? And obviously we're going to continue this onwards. For example, a3 will be equal to 1/2 of a2 plus 7 over a2, where a2 was this 2.66666 repeating number. And one can find that this is approximately equal to 2.64583, and so on. And one can show, at least via calculator, that that is a better approximation. And a4, one can find is approximately equal to 2.645751312, and so on, and one can show that a5 is approximately equal to 2.6457551311106, and so on. And it can continue going down and down and down, and you're going to get better and better approximations to the square root of 7. And again, how do we know that this is getting closer to the square root of 7? Because we've already proven that 1/2 of am plus alpha over an converges to the square root of alpha, provided that alpha is greater than 0, and our initial condition, a1, is greater than or equal to 0, 2, and both of those conditions met. Therefore, this is a decreasing sequence that's obviously bounded below, and converges to the square root of alpha. So we know that these numbers should be getting close to the square root of 7 as n becomes arbitrarily large, right? So after 5 iterations of this Mesopotamian square root sequence, we have that a5 is approximately equal to this term, right? And there's obviously some methods that might converge faster, but you should be able to show, at least via a calculator, provided that you trust calculators, that this is equal to 2.64575131106, and so on, right? So if you notice that even after 5 iterations, these numbers match to at least a 10 decimal accuracy. 2, 4, 6, 8, and 10. Obviously matches on the 11th, but this is a 10 plus decimal accuracy after 5 iterations, right? Isn't that nice? So if somebody asks, what is the square root of 7, you just do 5 iterations of this, and you can get 10 decimal accuracies, right? So it actually converges fairly rapidly. Right? But that's one of several different applications that you can use monotonic sequences for, and we'll discuss a few more in the near future. So until we get to that time in the future, hope you enjoyed this video, and I'll see you then. Take care.